So, as we're getting ready to look at some slope fields, let's look at the differential equations, because those are obviously related. But let's determine whether each of these functions is a solution of the differential equation y double prime minus y equals 0. Now, how am I going to tell if it's a solution?
If it's true, differentiate and then it should be. No.
I have a theory. So find the derivative. Subtract by the original. Substitute second derivative. Factor by the original equals 0.
Okay, so if you get the second derivative and you subtract the original function from it, you should get 0. Or in other words, the second derivative should equal the original function, right? So basically, we got to find out which of these functions will give us a second derivative equal to the original function. Okay? Yeah.
Should I just say the answer, or should we go through each one of them?
I think
Well,
we
let's-
go through each one of them and then find an answer so that we can show our work. Okay.
Let's try them all, okay?
Yeah, I agree with that.
Because we could have all three of these work, or just two, or one, or none of them, okay? So let's double check here. So what's y prime for a?
Cosine.
Cosine x. And how about y double prime? Negative sine x. Does that equal y?
No.
Nope.
It's not
All right.
b equals to y.
So this is not a solution. A is not a
the
solution.
solution.
Okay? So now how about b?
B.
What's y prime here?
So it's just you keep what's there and you take the negative of the x.
Okay. You write it down exactly as it is and then multiply by the derivative of the exponent, which is negative 1. So negative 4e to the negative x. Okay? Now y double prime. Yeah, again, same thing. Write it down exactly as it is. Then multiply by the derivative of the exponent, which is another negative 1. So that's going to make that positive. So that equals y. So B is a solution. Okay? And then we got to do the hard one here. C times e to the x. What's y prime?
C times e to the x.
And what's y double prime?
C times e to the x.
Yeah, okay, so that does equal y, so this is also a solution.
In my memory, we have seen the same problem for our time.
Have we seen this problem? I know we've done similar problems. You think so?
Yeah.
I don't remember.
That would be Akko Taco.
We've done a lot of problems. It's possible. So.
That we have. That we have.
All right. So then, let's look at this one here. We said for the differential equation, xy prime minus 3y equals 0. First of all, verify that y equals cx cubed is a solution. And secondly, find the particular solution if the initial condition y equals 2 when x equals negative 3.
So from the start, don't you just like to find the problem? Do we assume that y equals cx cubed is a solution or not?
Well, we need to verify that it is. How do we verify that it's a solution?
Put check mark next to it.
What?
Put a little check mark next to it.
Come on, you guys show.
We isolate y prime and then integrate it.
Yeah, find y prime. What's y prime here?
3cx cubed.
3cx squared.
Here's square.
I know what you meant.
Oh,
So,
and then plug that into the original equation.
so xy prime minus 3y has to equal 0, right?
Yeah.
Well, y prime, we just said was 3cx squared. And y is cx cubed, right? So that's 3cx cubed minus 3cx cubed, which does equal 0. And now we can put the little check mark next to it that we verified this is a solution. Okay? So now we want the initial,
Wait, Mr. Dixon?
yeah,
So, how, I see how you got, where'd you get the second, the negative 3, C, oh, because it's y, which is 3x,
yeah, it's minus 3y, and y is
cx
cx cubed.
cubed, not squared. I understand.
Okay? Yeah. Here's your y from up here. Okay.
I'm down.
Your y prime is this part right here that we got right there. Okay. All right, so now, how are we going to get a particular solution if the initial condition y equals 2 when x equals negative 3? How are we going to use that?
Do you just plug in 2 and negative 3 and find C?
Okay, yeah, if we plug in 2 and negative 3, we can find what c is, right? So, if 2 equals c times negative 3 cubed, then c equals what?
2 over 9?
2 over cubed.
What?
Cubed. Use the original y, not the y prime. So it would be x cubed. So it's over a negative 27. Okay.
Yeah, that's what I'm, that's exactly what I'm using. 3 cubed, oh, cubed, oh my god.
Yeah,
Cubed of 3.
that's okay.
Yeah.
That's okay.
Squared is 2.
Alright, so the particular solution then, the particular solution would be y equals a negative 2/27 x cubed. Okay? So there's our particular solution. Any questions? These really aren't too bad as long as you just remember kind of the procedure and don't get caught up in the fact that you're dealing with a differential equation. It's the same kind of stuff. You just, if you need y prime, then take the derivative of y. If you're trying to verify a solution, this is like the old back in pre-algebra when you solved an equation. You would verify whether your answer was correct by plugging it back in. Well, here you're just plugging in y prime and y and seeing if it gives you a valid equation. Okay? So, the next thing we want to do is look at some slope fields. So first of all, we're cycling back here to look at slope fields again. It's been a little bit it's been a little while since we've worked with these, but we have a slope field for the differential equation y prime equals x minus y for the points negative 1, 1. Okay, that's negative 1, 1. In case you can't read that. 0, 1, and 1, 1. Okay, so here's our x-axis. It's a little faint there. There's our y-axis. So, first of all, I'm going to plot each of these points. Negative 1, 1, 0, 1, and 1, 1. Okay? Now, what is y prime at the point negative 1, 1?
Negative 2.
Yeah, it's negative 2. Okay? So here, y prime is negative 1 minus 1, negative 2. So, you sketch a little thing like that with a slope of approximately negative 2. Okay? You can kind of think, alright, the point 0, negative 1 would be somewhere around there, so it's probably going to be like on that line, on that angle down there. Okay, so that's about a slope of negative 2. Okay, try to use the scale that's given to you on the graph to help you make it as accurate as possible. Okay? Alright, so then what about 0, 1? What's our y prime for that? Yeah, 0 minus 1 is a negative 1. So, if I had a negative 1 slope, it would be going from here to there, right? So I'm gonna draw it looking like that. Okay? I'll get rid of these extra little marks. But again, if you use the scale there on your graph, that's helpful. Okay, and then how about for the point 1, 1? Y prime equals, yeah, it's 0. Okay, so here it's going to be horizontal. Okay? And that's all you have to do. Don't let these are so easy, they're hard if you overthink them, okay? So that's all there is to it. Okay? Okay, so then we have some matching ones. It's really hard to see here, so you're going to have to look at the notes on your guided notes there, okay?
The x and y are the coordinates, and then the y prime is the slope.
Yes,
Easy peasy lemon squeezy.
that's right. Alright, so what's a key area that we could look at here on A that's going to help us?
The y-axis?
0.
Okay, y-axis 0, what do we explain?
Because it's like the horizontal, so it's like
Well,
y.
It looks like parabola, basically.
That's right. Okay, it does look like a parabola, and if you look on the y-axis, the slope of all of those points is 0. Okay? So, what else do you notice about all of these?
Those,
If they vary
for
with
every
the
x value, all the y are exactly.
Yeah, for each different x value, all the y's are the same. For example here, all of these are the same. So what does that tell me about my differential equation?
does not depend on the y value.
That's right, good. It does not depend on the y value. So look,
The only one is 2.
that one I can eliminate and that one I can eliminate. Now, I would want to verify just to make sure that it fits with my others, but you'll notice here, y prime equals x. Well, if I think about that, here x is 0 and they're all horizontal. Here x is 1 and they all approximately have a slope of 1. And over here at 2, they're even sharper at a slope of 2. At negative 1, they've got a slope of about a -1, okay? So that does make sense. Y prime equals x would be the differential equation for that. Also, if you think about taking the antiderivative of x would be x squared over 2, a parabola. What did we say this looks like? It looks kind of like a parabola. Okay? This one you could do that with. Others you may not be able to do that with, but okay? So let's look at the others. What could you use to help us out here?
We know that the third one only depends on y, so you can see which one only changes with the y, does not change with the x.
That's a good pickup there. Look, it's 0 right here on the x-axis, but also notice any value of y you choose, no matter what x is, the slope is staying the same, right guys? So because of that, we know that here the slope is not dependent on what x equals, which means which one of these is the differential equation?
The third one.
The last one, yeah.
And the first one depends on both x.
You're right. The third one does depend on x and y.
Sorry,
Another thing you can pick up on here is notice these zeros. Okay? These zeros are occurring. You could pick any one point, like for example, -1, 1. If I plug in a -1 and a 1, I get 0. Okay? So that helps me even more than just process of elimination here. That also helps me tell that that is the differential equation for that. Okay? Is that making sense? All right. Okay. Okay, so sketching a solution using a slope field. Okay? I'm going to assume you guys know how to plug numbers into an equation. Alright? You'll see this table. The only thing that may be different on, say, a test or a quiz or something is that maybe they don't give you the actual values in the third row here. Okay? But notice what we're told. We have a series of points here at -2, -1, -2, 1, -1, -1, -1, 1, 0, -1, 0, 1, 1, -1, 1, 1, 2, -1, and 2, 1. Okay, so if you want to plot those first, that might not be that might be helpful. Okay, so -2, 1, -1, 1, 0, 1, 1, 1, and 2, 1, and then same thing down here at -1. Okay, so those are the 8 points. But then you have our differential equation. Y prime equals 2x plus y. Okay, so 2x plus y, so 2 times -2 is -4, minus 1 is -5. So at that point, I have a slope of -5. Now how do you do -5? Just make it really steep, okay? It's all kind of relative, right? So I'm going to make -5 really, really steep like that. Okay? And then you'll notice at -2, oh wait, that was at -1, sorry. That's down here. Okay? At -2, +1, and also -1, -1, I have a slope of -3. So I'm making it just slightly less steep. Okay?
Is there any kind of formula where you plug in the slope and it gives you back something like that?
You plug in the slope and it gives you back what?
The angle?
Oh, well the angle if you remember, tangent of theta equals the slope.
Oh, that's.
So
to do the
if you want, you could do that, but I wouldn't recommend it. You just need to eyeball it. Get it close. Okay? So then the next two are both a slope of -1. This one's a little easier because I'll just aim it. If I aim from here straight at the origin, that would be a slope of -1. So I'll put that there. And I could do the same thing with this one down here. Those both have a slope of -1. And then at 0, 1, and 1, -1, I have a slope of +1. Okay, so there's a slope of +1. And there's a slope of +1. Then +3 and +3. So I'm making it steeper here. And then a +5 at my last one. Okay? So we just drew a slope field for that. Okay? Now, if we were given a specific point that we wanted to sketch the graph going through, we could use this slope field to help us draw this. So for example, if I picked a point, say right here, okay? If I were to look at kind of what that's between, like what things have the same slope that's between. Notice here, this and this, if I drew a line between those, it would kind of be right between those. All right?
What do you mean?
So if I'm,
Thank you.
see how these both have a slope of -1?
Yeah.
And if I drew a straight line between them, I have this point here. Okay, so the slope of any of the function at that point is going to be about a -1 as well. Okay, now again, this is not a perfect, it's not going to give us a perfect sketch, but it's going to give us a good idea of what the graph would look like.
Wait, I don't really get what you're saying by that.
Slope of -1, slope of -1. If I drew a straight line between them, the point that I'm working with is,
Like an approximation of.
yeah, it's an approximation, okay? What we're doing here is we're going to say sketch y going through, let's see, that's the point, -1/2, 0. Okay? Now, same idea here. Notice here's +1 slope, +1 slope. So, looks like between those two, I should have a +1 slope. Which means somewhere between them, I should have what as a slope? 0. Now, do I know exactly how far down it goes? No. But, this does at least give me an idea of what that's going to look like. Okay? Now, also between those two, I'll probably be at a slope of +3. So notice here, this is going to continue to get steeper and steeper like that. It's going to be about like that. Okay? And that's a rough sketch of what this graph might look like. Okay? If we had chosen the point 1, 1, it would look something like this one over here on the right. Okay? Here's 1, 1.
Mr. Dixon, why did you sketch it going through -1/2 and 0?
I just picked a point. We could pick any point and use this slope field to help us solve, or help us sketch it. Okay? So we'd have something kind of like this. Right.
So both the red and the y and the three lines are graphs.
Yeah, that would be the graph if we were going through 1, 1.
Oh.
Here's the graph through negative a half, 0. They're all gonna be the same shape. It's just a matter of where they're moved around.
Is there not impossible to know?
Yeah, they'll be vertical translations or translations of each other. Okay?